Well, hello everyone, and today I will be recording part 7 of my series on DLL injection into all processes, and today we'll be continuing to code our injected fake.DLL, and today we'll expand it a little bit. So let's go back into our coding environment. Let's fire up Visual Studio, and here's our InjectAll project. So if we look into what we left on what we've done last time, we basically coded a scaffolding for our fake DLL, which basically has DllMain that creates a logging entry, and it basically calls log to file formatted, that calls log to file, and it basically uses ntdll to write into a file. Very simple. So today I want to expand it a little bit and show you, first of all, how you can test this DLL, because obviously you can't run it. You need to actually you can't inject it into all files. You need to test it first. Now to do that, I usually create a simple console application as a separate project, and what you can do, you can just type console, and we're not looking at C#, but instead console app C++ for Windows, and for the lack of better name, let's just call it TestConsole. And I also create the same kind of a stuff for a production application, because you don't really you're not supplying it for anyone. It's just a little test environment, and we need Windows header obviously to do work in. And let's see, what else do we need? Well, at this point, let's just try to call our application, and let's see, include our shared definition here, and let's just say shared definitions. And the reason we need that is because we might need some file names here. And let's code it as debug. And at this point, let's just try to simply load it. Simply load our DLL. Oops. DLL name, and well, let's just use our injected DLL name like so, and we will use simple WinAPIs here to do our injection. So hmod load library, specify the name. Oh, and by the way, we need to make it into large. I'm sorry, not large, into Unicode. And if that succeeds, we need to free library. And that's pretty much all we need at this point. So now, to make sure that we can break on our DLL, now for instance, if we are, instead of just doing this, let's say if we want to try the release build of our DLL, so we're providing a relative path. Let's make sure that we have everything set up for release. Let's rebuild solution. So that will create a release DLL for us. And if we go into DllMain, let's say if we want to break before we do our logging function, the way we can do this in a release build is by using debug break macro, and that will put a user mode breakpoint. So let's build it again, and let's say here we are actually in a debugger build of our test console. So let's rebuild it and see what happens. So I put a breakpoint. Oh, by the way, sorry, we need to set this project as a startup, because obviously right now the startup is our driver, which, well, we can't start. So we need to set this one as our start project. And let's see, I need to find it. Here we go, start a startup project. Now we can actually start debugging. And what would happen here, let me just expand this a little bit. If we load library, we should generate a breakpoint. Here you go. So we just broke on the breakpoint. And what we can do, we can just keep going. So at this point, we have our debug line, so we can step into it. And we can actually go here. Then we can step into our file here. And by the way, because we are in a release build, it's actually not, you know, that we couldn't really step through the source code. So what I'm doing here, I'm kind of toggling to disassembly. You can do Control F11 to do that. And then we can actually see here. Let's see, so we are, oh, so what happened here is that this function has been inlined. So as you can see, there's kind of like, you know, two errors, even though we didn't step into it. Well, the compiler inlined this function. So, and right now we are calculating the length of the file. So we need to just run to cursor. Oh, and well, I screwed up because I hit the wrong button here. So at this point, we just created our file. So if we continue running and we go, well, you know what? We did not create a file. Okay, you know, I totally messed it up. So let's start over. First of all, we do not have our InjectAll folder, so we need to create it. Like so, because again, we have it on our test environment, and right now we are in our production environment. Now I don't like really working with release configuration, so let's not deal with debug break. You would normally do this if you want to catch a breakpoint somewhere in release build in some weird situation and catch it, let's say, with some other debugger. But here we don't really need it, because all we can do, we can just build a debug version and just put a breakpoint here. And wow, what happened here? We got a bunch of errors somewhere. Let's see, DllMain. Now, why is it doing that? Okay, well, need to look into this. So all of a sudden, we are having a lot of issues here. So let's take a look. Oh, well, what happens here is that we did not add our input library, ntdll.dll. So let's see if that would help. Okay, and it would. Let's do the same with 32-bit. Let's rebuild it. And again, the same issue. Again, all we need is just to be able to build these. We're not going to be running them in the production environment. Okay, and that works. So let's go back to 64-bit, rebuild. And let's go back to our console, and in this case we will just call or load the same DLL of the same bitness. So in this case, let me show you how easy it is to step into breakpoint. So if we step over, our breakpoint actually hits, and we can step into, and we can go and trace our file. So right now we can go in, so we can actually see the output, and this is just a this message of hello world that we can tell is coming from InjectAll FAKE.DLL, which is 64-bit, and we calculate the length, which is 35 symbols. Okay, so now we convert. So here's a good example. We convert from C InjectAll log inject.all.txt into a Unicode string. So, and here, as you can see, it's kind of the same thing, but with addition of this, prefix here. Again, we can't assume that this will be always like this, so you have to, call an API to do that. So we have this function, and then we call ntcreate file. It creates 0. We write file, we close it, we release string, we return the status, and we are done. So at this point, we keep going, and again we returned here into actual CRT, which we kept in our debug build. But now if we look in our folder, we have a log file. Now, to make it a little bit more interesting, it would be actually nice to add some additional information, because just saying hello world is not going to be that interesting. So let's add something like process ID and also the time, and maybe we can actually get the image name for the process that we are running in. So let's code it now. Okay, well, finding a process ID using Win32 is somewhat easy. Well, the problem is, like I told you earlier, that we don't have Win32. All we have is just a native subsystem, which is ntdll. So how do we go about this? Well, we can actually use something which is called a TEB. So if we get a pointer to TEB, and this is a thread environment block, we can actually access it, and it can give us some information on the process ID and also the image name that the process is running from. Now, it's mostly undocumented by Microsoft, so we'll have to actually, because you see how huge of gaps it actually has. So if we look deeper into undocumented offsets here, we can actually get that information. But before, we actually need to get a PEB from our process. Now, this is relatively easy. Let's just create a function that is called getTEB, and let's just say that it returns a pointer to TEB for the current thread. Now, the TEB is kind of well documented online. It's not documented well by Microsoft, but it is a well-known structure. It's a structure that is provided for a thread environment block. Every thread has it. So we can actually access it. Unfortunately, we have to use intrinsic, and they are specific for the bitness. Let's just say else. If we have Win32, and otherwise it's an error, unsupported CPU, and if. Okay, so for 64-bit, we can use a special register. Now Microsoft stores it into special register for every bitness. Now for 64-bit, it stores offset to so-called TIB in the GS register, and we can access it by using intrinsic, which is called red GS keyword. Okay, that's this one. And what we need to do here, we need to do the offset of macro, and this is the structure ntTIB, and we need its self pointer, and then we need to cast it into ulong, and that will obviously need to be cast into TEB. Now this is very kind of like weird way of putting it, but basically if you look at the structure here, the TIB is an internal structure and we need reference to self. So in other words, that will give us the offset where the TEB is stored in relationship to this GS register. And if we switch to x86, kind of would do the same thing, except that we do, I'm sorry, not else, we need to get here. Here we need to read FS D word, because we're in 32-bit. Again, ulong, ntTIB self, and we cast it into thread environment block. This is just the way Microsoft coded it. It's, again, this FS register holds a, well, kind of like a pointer to this ntTIB structure, and then at this offset, it actually holds a reference to a TB. So this is just, you know, kind of like intrinsics pretty much. So there's really nothing to think about here, but what's important for us is that it gives us the pointer to TB. And let's remove all the spaces. And also we need process environment block, which is actually more important for us, and we can get it from having a pointer to TEB. I'm sorry, to thread environment block. Okay, so, and here we return pointer to PEB for the current thread. Okay, and this one is very simple. We just take TEB and we need process environment block. So that's pretty much it, and that's how we get PEB. Now, TEB is not as much of an interest for us here as it is the PEB. So that's kind of our goal here. Okay, so at this point, having these two functions, we can actually use them. First, we can get pointer to TEB, and by the way, before we can do anything, we need to declare them over here for forward declarations, I think it's called. Okay, so we get TEB first, then we have process environment block, which is get PEB, and we provide TEB into it. I know it's really confusing. Okay, so now having PEB, we get current PID, and the way it is stored in kernel, it's stored in the structure which is called client ID. And the way we can get to it is by doing this little play here. Let me just show you. Now it's also undocumented, so it might kind of a change in the future, but at this point we will rely on it. So first we need to cast our pointer to byte so that we can add actually byte offset, and then we need to add a size of TIB, and then size of another pointer, and then we will get our client ID offset, and that's the process ID, and then we can just simply get our PID, and that is called unique process. So that's the process ID, and we need to cast it, by the way. First we need to cast it into ulong pointer, and second time we need to cast it into ulong, and we will have our process ID. So it's pretty much that simple. Now we can also get a let's get current time. This would be nice to actually log the current time when the function was called. So for that, we will use nt query system time. That's the function, and it takes large integer, and let's just null it out. That will contain our system time, and we put it here. Then we need to, now when this function return the system time, it will give us in ticks, which is not really ticks, it's 100 or 100 nanosecond intervals, you know, like really low resolution tick number, since the computer was no, not since, since like certain epoch. I can't remember exactly, but you know what, we can probably look it up. Let's see if we go and look up this API. Okay, it's 100 nanosecond intervals since January 1st, 1601, and the main point is this is UTC. So what we need to do next to get the local time, we need to call a function which is called RTL system time to, let's see, to local time. Now why is it not here? Well, probably Microsoft did not define it or declare it, so let's do it ourselves. Now let me see, I think we have, yep, we do have this section for undocumented functions. So let me quickly add this function as well. So I'm going to add it here. It just basically takes system time and returns local time. And so what we do, we just call system time, and the second parameter will be local time. And to save space, let's just use the same input and output. Okay, and then we can use RTL time to time fields. And again, it's not defined or declared. So let me quickly do copy and paste into our DLL types here. So again, very simple API. It takes system time and returns as the time fields breakdown. Now I see that the time fields is also not declared, so we need to also add it. I'm going to save you guys time and just quickly copy and paste here. This is very similar to system time in Win32, which is exactly the same thing actually. And as I can see, they didn't declare C short. I'm not sure why they call it C short, but we'll just stick with it. Okay, so at this point we need to declare this thing into our code here, and basically what we'll call it is just let's see, TFST. Let's null it out, and input would be our system time, and the output would be our TF system time. So at this point, this structure would have the current local time, and we can use it. Okay, so now we have a situation. I told you before that we cannot really use structured exception handling here, because again, we are very limited in our capabilities here. And since we're using a little bit of undocumented stuff here, we have to be careful. And let's just document it here. We can't use structured exception handling, so we need to kind of have a little bit of an if statement here and see if we have the process parameters pointer. This is part of PEB, but if something failed here in our calculation, this pointer will be, wrong. So in that case, we have no path to the image file, and in this case, we can simply output where we ran from. And what we will do our debug print line, and we will do it like so and provide all the parameters on the next line. So first, let's output our year. Apologize, like this, as an integer, unsigned integer with at least four digits. Then we can do the same for months with 2 digits. The same for day. Then we put space. This is hours, minutes, seconds, and milliseconds as 3 decimals. Then we put a PID as an integer, and then inside we will provide our Unicode string, which will be an image path. Okay, and now we need to provide those values. So here we have a year, then we have month, then we have day, then we have hour, then we have minute, then we have seconds and milliseconds. Then we have PID, which is UI PID that we calculated above. And then we need to provide a pointer to process parameters. And this would be image file name. Okay, so this last specifier will need a pointer to Unicode string, which is this here, and that is the image path name, which we can get from the PEB. And exactly the same thing down here, except that we don't have a path. So we can just say no path, and this parameter we cannot use because this is null. Okay, well, let's see if it builds. And it does. So at this point we have a breakpoint, and let's try to see what happens. Again, we start from our test console and we break on load library. Let's step into it, and we break here. Let's get PEB. You can see we got values here, and get TB. Let's see, we got a process ID, which is 332. And just to verify, we can run Task Manager and go into details. I can't use Process Hacker because I don't have it installed here, but basically now we need to find, let's see, which is TestConsole. Scroll all the way down. TestConsole, and the process ID is 332. And as we can see here, this is our process ID, so we got it right. Now let's get local time. If we go through all the fields, this one here will have year, May 19th. This is 9:41 p.m., exactly like we have here. So this is correct, and let's see, and we actually have PEB here, and then we can output it into a file and exit. Okay, well, let's see what happens. So we have log InjectAll, and what do you know? We have the actual process ID, we have the DLL name that we ran, and we have our path to our process that we were running from. So perfect. And basically, if we run it again, we will create 2 entries here. So, and this will be our log file. Now I have to point out that obviously I'm not doing anything fancy like you know, checking the size and truncating it. So, you know, keep this in mind. Don't make this test run for too long, because it will basically create an uncontrollably long file. So again, keep this in mind and just periodically delete it. Okay, well, there is also one thing that we need to do in our little test console, which is this one, and this is concerning our folder here. Now, as you can see, we will be running our little logging function from the DLL and right into that file, which is, you know, hard-coded here, as you can see, into this path. Well, this folder here actually have to be accessible for pretty much any process. Now, some people would say that if you go like properties, if you go security, and let's say edit, then you add, and then you go everyone, check names, right? And then you kind of give everyone full control and apply. Well, you would think that that would really give everyone full control. Well, the problem is that it won't. It will get every user on the system full control, but it will not give full control to a process that runs with low integrity level, or they call it mandatory integrity label, I think. And that process will not be able to write into this folder, even if we have access to everyone. So we can't really give access to it through this Windows Explorer. It just won't work. So we need to code a little helper function here in our test console to actually give to set security descriptor on that folder. So let's do it right now. Now, because we are coding in test console, so we don't really care about any of the code, you know, accuracy. I mean, not code accuracy, but any high efficiency of this code. So we just kind of code just to make it once and not worry about it later on. So let's just say folder path, and what will happen is that this this function will be called from our test console, and it will set a security descriptor on this folder. And to generate this security descriptor, we can use this API with a very long name, convert string security. You know what, it's not even coming up through IntelliSense. To make sure that it does come up, we need to include one header, and this is sddl.h, and now it should be able to come up. What I usually do, I start with double quotes, and then I can just go and start typing. So basically, let me show you. Let's see, if we go and do convert string, see, like this stuff, we need convert string security descriptor to security descriptor. Yeah, good luck typing it all. And what we have here is basically a string that will specify security descriptor, and then we have to provide revision, which is always 1, and we have to provide security descriptor, and let's see, security descriptor size, which is not very important. And let's see, so here we have pointer to security descriptor, and originally it is null. And then we have ulong, and we have this, which is also null. And then if this succeeds, we actually have our descriptor, which we need to free with the call to local free to release memory. And over here, let's just do printf, and it's a wide string. Let's just say error, put an error here, and set the name of the API that failed, and let's just say get last error, and let's specify the file path. Let's see, file, and let's just do like so. Okay, so at this point we can create security descriptor. Now I'm going to do copy and paste to kind of like do it real quick, so I don't want you to type all this stuff. Now this thing, I know it looks horrible, but if you Google this API here, let's just do it real quick, and provided my internet actually cooperates. Okay, so they have a string format here. It's a special language that Microsoft uses, so it's kind of like long document here, and it kind of they explain all the stuff. And then what's important for us are those ACE strings that, you know, a lot of stuff here. So just to go quickly, I'm going to do another copy and paste just to show you what this string does. So this D, it stands for DllMain, and S, because you see it kind of splits it up into segments. So here's one segment. I'm sorry, here's one segment, and then here's the second segment. So first D stands for DllMain, and S here stands for SACL, and then A stands for access granted, and ML stands for mandatory label. And that's what we need to create in our security descriptor. Then GA stands for generic all. See, like it's pretty much everywhere. And then this actually last segment here stands for everyone. This one for anonymous. This one is for this SID. Stands for all app packages. That includes like UDP apps and stuff. And this one is an undocumented one, which is the same as app packages, but restricted ones. Microsoft provides some documentation for this, but it's very scarce, so I kind of like wrote it down here. And this little SID stands for untrusted mandatory level. So what this does, this SID basically gives access to all of these things. So it's not just everyone, like we could do in Windows Explorer to give access to generic all, but it also provides all of these access to all of these packages, and also gives access to untrusted mandatory level, which is what we need. So in other words, it makes the folder, our InjectAll folder, accessible for pretty much everything. So right now we need to actually grant access or grant this security descriptor or attach it to the folder. And then at this point we just use simple Windows APIs. So create file. I know it's kind of confusing, even though we are calling create file, but we're actually opening a folder. So now desired access, now this is important. We need to be able to write DllMain and also write owner, because again we'll be changing stuff here. Now you can get this from the documentation. So let's do file share delete, file share read, file share write. So it basically provides sharing for everything. Now there's no security attributes. We're not setting it here because we're just opening it. Open existing. And what's important is to specify file flag backup semantics, and the last parameter is null. Now this little flag is necessary to open a folder. This is important. Okay, so here we have a handle to our file, and we check to make sure that this is not invalid handle value, and then we close that handle. Make sure to do that, otherwise we have an error. So let's just copy here and paste, with the difference that this is create file, and here is the file path. Okay, so here we need to actually set our DllMain, and we will use another API which is well documented. Set kernel object security, and we specify, you know what, it's not a file, it's a folder. Let's name things right. Let's make a little space here. Okay, so we specify our folder handle. Then if we go into to this actual API, into the documentation for it, we need to see which flags we need to specify. And security information right here. So we need DllMain security information. So we specify that. And we also need, because we're setting mandatory label, we need label security information. Okay, and then we provide our descriptor. At this point, if we succeed, now we can just reuse this and say success. Set DllMain, actually no, set SD security descriptor, and we don't have an error, but we have a file, and otherwise we actually need to output that we failed and pretty much output the error code. So let's compile it. And as you can see, it works. So all we need to do is just call it on our file. Now we don't need this because, you know, we tested it already. And right here, we need to actually get to our folder. I'm just going to do copy and paste here because I'm lazy and I don't want to type it. Make sure we have 2 slashes here, and let's see what happens. We build it, and we need to run it. Let's step into it. So we created our security descriptor. It's right here. And we failed to open our file. Well, let's see why. And the error code is 5, which is access denied. Well, how about we do it this way? We build a release of our console, and let's go into C++, InjectAll x64 release, and here it is. Let's copy the path, and then we need to run command line elevated. And then we need to change directory into our path. And then let's see, what is it called? TestConsole. Not PDB, but console. Let's run it. And success. We just set security descriptor to our InjectAll. So let's see if it works. So if we go into Properties, Security, as you can see, we set security descriptor to all these entities that we couldn't, I mean, we could have set these, but it doesn't even show the mandatory integrity level. So it doesn't provide here. But the bottom line is that now we can actually run and write into this folder. Now, and I mean write from any process that runs with low mandatory integrity level, which is what we needed. Okay, well, in this case, we don't really need this folder, to be honest with you. And the reason we did this here is so that we can run this test console on our test VM. So let's copy it there. Let's just put it here on the desktop. And what we need to do, we pretty much need to do the same thing. Let's copy its path. Let's do command, run it as administrator. So let me type my password. We need to change to desktop, then test console, and antivirus thing kicks in. It thinks it's a virus, so let's let it think it through. And here you go, we set our security descriptor. So now if we go back here and if we run it, we check security, and here you go, we set this up. This is what we needed. Now it has to be done once. Obviously it's not, we wouldn't run it in a production code. It's just kind of like my way of showing how you can run a little bit of a test app to set up your environment. Now we need to do the same thing here for our 32-bit testing environment. For now we don't even have a folder, so let's create it. And InjectAll, make sure to name it the same. And what we need to do, we need to go back into our coding environment. We need to change bitness. We need to rebuild our console for 32-bit project. And let's go back, release, and test console. I'm going to copy it and then paste it into our test VM. Let's do the same thing. Okay, so let's get the path, command line, run as administrator. Okay, well, what's going on? Doesn't like the password, or maybe I mistyped it. Oh, that's a different account here. Okay, so very monotonous thing, but pretty much the same. Need to run it, and let's see, again, the antivirus kicks in, so I guess it wants to check, and here we go. So we succeeded, and let's double check security, and here you go, we set this up. Now again, this will be necessary later on. We have to do it only once, and so we can go back into our test environment. And we don't need this function anymore, so technically we can comment it out. It served our purpose. And at this point, we can bring this back so we can actually test our DLL. And well, let's look at the DLL. Well, the DLL is also ready to go. So what it will do, again, it will simply, when the process is, when the module is loaded, we will get our DllMain called with DLL process attached, and it will put this little line into a log file that will tell us the time, local time, the process ID, and the image name for the process that we injected into. And this will pretty much prove for us that our DLL was injected there. Okay? So at this, I think this concludes our creation of our DLL. And on the next stage, we will actually go back into our section. If you remember, we were creating known, we were adding our DLL into known DLLs. So for now, we have our DLL, and now next step would be to actually go back to kernel and add it as a known DLL. Well, for now we will stop because this video is kind of long. It's almost an hour, and I will do it in the next installment, in the next part of this tutorial. So guys, I'll see you then.